S. Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
Stoichiometry and calorimetry is one of the critical application area of applied thermodynamics. Welcome to S. Chand Academy, and I am Dr. Anmol Bhatia. In this video, we will be learning the concept of calorimetry and stoichiometric concept of thermodynamics.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
So, the topic that we are studying is calorimetry and stoichiometry. Firstly, we will be starting with calorimetry concept, and this calorimetry is basically a scientific way of measurement of the quantity of heat. And we want to measure the heat for certain critical applications, and why or how do we measure that heat? That is particularly done with the help of a special instrument, and that instrument is calorimeter. So, calorimeter is a device which is particularly used to measure the heat. So, how can it be done? That we can see herein. We have to have an assumption which is heat lost is equal to heat gained by the system, which is in the negative quantity. That means in simple calorimeter there is no heat which is lost to the surroundings. So, when we specifically say that heat lost to the system is equal to the minus times or the negative value of the heat gained by that particular system. So, there is one of the aspect of this calorimetry which is called as coffee cup calorimetry, and herein we use styrofoam instead of a beaker to keep the heat inside. So, what we do, we have a beaker in general, but we use styrofoam in order to do not allow heat to escape out of that system. Okay. So, what are the basic steps here? So, we need to add hot solid metal to the cool water. Now, what happens? The water will heat up and the temperature rise as this metal cools up, and eventually water and metal would be at the same temperature. So, the heat for the metal is equal to the heat for the water plus the summation of both, and that is equal to 0. So, you can see that the heat which is lost by the metal equals to minus times the heat which is gained by water. So, this is the concept while measuring or checking. So, herein you can see that the heat lost by the metal is equal to negative times the heat gained by the water. In calorimetry, this is the basic concept in which heat lost by the metal is equal to heat gained by the water, and Q or heat here is mc delta T. So, you can basically see that Q for the metal, it is generally mass into specific heat into the change in temperatures, and this small m indicates the case for the metal, and negative times the heat gained by the water, that is mass into specific heat into the change in temperature for the water value. So, mass of water, specific heat of water, and the change in temperature for water. So, this indicates that we can do calculations, and if in a particular numerical you are supposed or you are required to find out that we have a metal and there is water, and we need to find out what is the specific heat of that particular metal, we can do it easily with the help of this simple calculations. So, we look at that simple calculation with the help of a numerical problem. So, you can see that in the numerical problem it is saying that a 358.11 gram piece of lead was heated in water to 94.1 degrees Celsius. That means there is a change in temperature of lead and lead by putting it into water. So, it is removed from the water and placed into the 100 ml of water in styrofoam cup. So, we have a coffee cup, that is basically the styrofoam cup, and the initial temperature of the water was 18.7 degrees Celsius and the final temperature of the lead was 26.1 degrees Celsius. So we have temperature changes in case of that metal and we have temperature changes in case of water. Now the data is asking about what is the specific heat of the lead according to this data. That means I have already told you the process in which we generally undertake that the heat which is lost by the system is equal to the negative times the heat which is gained by that particular systems. So we'll use that particular concept. Firstly understand that what is the concept. So you can see that the heat gained by water, that is mass of the water, specific heat of the water and change in temperature of the water. This is mentioned, the symbols have the usual meanings, and the heat lost by the lead, that we need to keep equivalent. So for the lead, this is mass of the lead, specific heat of the lead and the temperature lost or the temperature change for the lead case, wherein the symbols have their usual meanings. Now in case of that calorimetry aspect, we have to take an assumption that the heat gained by the water is equal to heat loss. You can no doubt put in the negative sign that indicates the heat loss, but we can skip it in the usual scenario. So we can generally keep these two equations equivalent and majorly we have everything, but we need to find out the specific heat for the lead. So we have all the other aspects available and we can put all these values together so that the specific heat of the lead can be calculated. Okay. So what data we have? Mass of water, which is 100 grams. Specific heat is mentioned to us in the question. Change in temperature values, there were two temperatures mentioned to us. So we have converted that temperature value by subtracting them. And mass of lead is mentioned to us. Change in temperature of the lead is required. So negative value for the change in temperature. Then we can substitute all these quantities in this particular equation so that the specific heat value can be calculated. So this is the final result. You can generally skip this negative sign for the specific heat value. So this specific heat value can be calculated from that calorimeter aspect, right. So basically a device which is used to find out what would be the heat, so that can be generally determined with the help of this process. So there is one instrument which is called as bomb calorimeter, that is specifically shown here, and constant volume bomb calorimeter is basically there, that burns sample in oxygen, and herein we generally we get some heat from the reaction that warms the water. So specific heat context, we can calculate the heat which is Q water is equal to mc delta T in case of water, and that reaction for the bomb is specific heat into the temperature. Then this particular aspect can be used and that can be put equals to 0. Herein the geometry basically states that you have an ignition wire wherein you have a sealed bomb and the oxygen is being there. So as I have told you that we burn the sample in the oxygen, the sample is burned in that particular oxygen, and apart from there you have water. So heat which is released from the surface, it heats this particular water. Additionally, there is a motorized stirrer that continuously stirs this water and the temperatures are basically noted, and this particular thing is there in the sealed container. So this is one of the calorimeter which is used to measure the heat. We stop here for the short break. After coming back from the break, we will learn the concept of stoichiometry.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. Before going to the break, we have learned the concept of calorimeter. Now, in this part, we will be learning the concept of stoichiometry, and there is one particular law that governs stoichiometry, and that is Hess's law. So, we will be learning that concept now. So, before going to the concept or the numerical aspect of that stoichiometry aspect, we will look at the concept in which we will be representing that specific chemical reaction. So, let us say if it is an endothermic process. So, there are two ways of representing an endothermic process. Let us say hydrogen and this iodine combines to form hydrogen iodide, and we want to show that what is the heat being supplied to the systems, that can be delta H, which is 53.0 kilojoules, and we can write this delta H separately, or second way of representing it, we need to include this with the reactant side. So, plus 53 kilojoules will indicate this as a representation way, or the way of designating an endothermic reaction. There is another way of representing an exothermic reaction. Let us say we have this reaction in which methane burnt into specifically into this carbon dioxide and water products, and half are the cases. So, you can see then when we balance it out, so this half can be, this entire equation can be multiplied by 2, so that it becomes CH4 plus 2O2, that gives you 1 mole of carbon dioxide and 2 moles of water. So, this is the case, and when this heat value is represented as a negative quantity, that indicates that the heat is released from the end product of the reaction, and that specifically indicates that it is an exothermic reaction. Otherwise, you can represent or add this particular part in the product side. So, half CO2 plus water plus this value, that indicates an exothermic process. Okay. So, summarizing, you have two signs. For endothermic, you have a positive sign of delta H. For the exothermic reaction, you have the negative sign of delta H. Now, we have an important designation of the physical states of matter, and when we change the heat of reaction, then this can be converted into the newer states of matter, and they are specifically solids, and then we heat it more, we will get liquids and then gases, and ultimately we will convert it into another state of matter, that is plasma. So, this heat plays a major role in conversion of one state of matter into another state of matter. Now, we have thermochemical equations, and in thermochemical equations we have coefficients, and those coefficients stands for what? Let us say we had this equation which was methane. This reacted with oxygen to form this carbon dioxide and those water, and specifically it was mentioned that there was a quantity which is half lying there, half. So, when we put in this half part, so the equation gets balanced. You would look at this carbon which is half the value, and when we multiply both these two, we will get oxygen as 1, and here also we have 1 oxygen. So, you have 2 molecules of oxygen just to balance the oxygen part, and this half multiplied by H4. So, when you multiply these 4 and half, you will get the value 2, and hydrogen also you will have this value of 2. So, that this equation gets a balanced one. Now, if I multiply the entire equation by 2 so as to have remove that fractional value, so I need to multiply the entire equation by 2 so that these two numbers can be removed, and ultimately you will get 1 here, 2 here, you will get 1 here, and you will get this value 2, right. So, you have the coefficient of this particular part as 1, you have the coefficient of this part as 2, coefficient of this as 1, and coefficient of this part as 2. So what does these coefficient means? These coefficients generally means number of moles, as you write it before that particular substance. So we may have these fractional coefficient also that I have shown you, and the process also to convert those fractional coefficients into the non-fractional ones. So this is one of the aspect of the thermochemical reaction. Now we will talk about stoichiometry, and in stoichiometry we will be specifically dealing with calculations of that heat, and we will learn the stoichiometry aspect with the help of this numerical problem. Okay. So delta H would serve as this stoichiometric quantity, and you will have this equation. It is given that you have a reaction below, and how much heat is produced when this 15 gram of nitrogen dioxide is produced, and you have this particular reaction which is 2NO plus O2 gives 2NO2, and this is a gaseous reaction, and delta H is mentioned to us as a negative value. That means the process is an exothermic process. So what we need to do, this is the initial reaction that you can see, and firstly what we need to go with, we need to calculate the moles of NO2 produced. So the molar mass of NO2 is this much. This molar mass can be calculated from the general convention, which is 1 into the mass of nitrogen plus 2 into the mass of oxygen, so that this value can be calculated. So the number of moles can be calculated by dividing this value produced, this mass produced, divided by the number of moles. So divide by the molar mass of the entire nitrogen dioxide. So 0.326 is the number of moles of that nitrogen dioxide which is produced. Now you have the coefficient of nitrogen dioxide as 2. So if the coefficient is 2 and there is a balanced chemical reaction, so you need to produce 2 moles of nitrogen dioxide for every 2 moles of nitrogen oxide. So what we'll use this stoichiometry chemical stoichiometric reaction to find out the amount of heat produced. So given value, you will have this delta H part as minus 114.1 kilojoules for 2 moles which are produced. So this value is being basically given for the 2 moles of nitrogen dioxide which is produced. Now we have to find out the proportion of the heat which is being there. So what we can do, we can set up a proportion which is 0.326, which is there, moles of NO2 produced. So what we will do, we will divide it by 2, because this particular thing is produced for the 2 moles case. So we will specifically go with the production of this nitrogen dioxide value. So what we will do, we will divide this minus 114.1 kilojoules, will divide it by 2 moles because the coefficient is 2, and we will add, we will specifically multiply it with 0.326, so that we can get this heat produced value. Heat produced which is specifically produced for the nitrogen dioxide case. So this is the particular aspect of calculating the heat produced for this specific case as per the stoichiometric analysis. So in the stoichiometric analysis, we have to go with the calculation of number of moles initially, and then we will need to look at the coefficient. So if the coefficient is 2, as in this particular case, so we have divided that coefficient with the total amount of heat produced and multiply it with the number of moles that we got from that general convention. So this is particularly the stoichiometric analysis. Now there is a particular law that governs, or that is particularly used when the stoichiometric analysis is being considered in terms of the thermodynamic aspect. So what is it? It has this heat of reaction which is delta H, and that delta H is constant whether the reaction is carried out directly in one step or indirectly throughout the number of steps. So when the reaction has number of steps, let's say you have that particular reaction in the previous situation which has particular steps. Now if those steps varies, Let's say the reaction was formed in 2 steps. Then also the total value of this heat of reaction, which is delta H, that remains the same. And heat of reaction can be determined by summing up all the heat of reactions of the several steps. So if you have 2 steps, then you can have individual heat of reaction in each step, and then you can add it up so that the total value of heat of reaction can be calculated. This is particularly for an example. Let's say this hydrogen and half of the oxygen is there, and water is produced plus this amount of energy is released. That means it's an exothermic reaction, and you have 2 molecules joining together, and the heat is produced, which is this delta H value. So this is one of the case of formation of water. Now making this particular aspect, if it is there making liquid from 2 exothermic steps, then the sum of those 2 would be the total of the heat of reaction. Let's say the same particular equation, if it is divided into 2 steps, let's say hydrogen plus half the oxygen will give you water, and when this water breaks, it against water is a gas, and when it is converted into this liquid water, then 44 kilojoules of energy is released. When energy is released, then it gets condensed into liquids. So you have 2 different heat values involved, and when you sum it up, you will get the total coefficients and the total value of heat of the reaction. So 2 reactions summed up, 2 different heat of reaction summed up to give you a final value of heat of reaction. That is this Hess's law. So we will have this numerical presentation, and this states that you have 2 reactions and 2 heats are involved, and you need to determine the heat of reaction for this particular case. So this is the final case in which carbon plus half of the oxygen gives you this carbon monoxide, and you have 2 reactions. So we need to find out the aspect heat of the reaction for this. So firstly, what we will do, we will have this particular reaction, which is this reaction, that is carbon monoxide plus oxygen gives twice of 2 moles of carbon dioxide. So this is 2 moles of carbon monoxide plus oxygen gives this value, and delta H is given for this as minus 577 kilojoules. Now we would be interested in finding out this carbon dioxide breakage, because this was asked in the question. So we would be particularly interested in getting this carbon monoxide on the product side. So we will basically reverse this equation. So this comes out to be carbon dioxide gives that reverse reaction in which heat of the reaction is 577 kilojoules. Now we are given with that reaction in which the heat value is minus 393.5 kilojoules, and you have this reaction in which carbon plus oxygen value is carbon dioxide, which is delta H minus 393.5. Now what we will do, we will multiply the entire equation by half, and we will understand why we have multiplied it with half. So half of this carbon plus that half the value of oxygen, that will give you half value of this 1 by 4 value of this oxygen, because it is already having that value. So what we will do, this 393.5 will become half again. So the value, the total heat of the reaction will become half. Now we will add the 2 manipulated reactions, which is this half of this carbon plus 1/4 of oxygen and plus twice of this carbon dioxide, that will give you the half of this carbon dioxide value, twice of this carbon monoxide, and the total value. So you can add those 2 equations, those 2 values. So one is 393.5 divided by 2 and 577 kilojoules. So you will get this particular value. Now what we will do, we will simplify it so that this particular reaction comes in, and ultimately you will get to convert it into a particular ratio. so that the final equation comes in. So final value is 183.5. As per the Hess's law, it states that the sum of the two will be the total heat of the reaction. So this can be clubbed, or that can be final value of the heat of the reaction. So with this we come to the end of the video, in which we learnt about stoichiometric analysis and the Hess's law with the help of numerical problems. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.